remember I was talking about Q being this way versus this way. Well, what if someone builds an experiment that's tipped over by 45 degrees? Well, then their Q is going to be different from your Q, and you have to map into them. Whereas here, you can actually come to a single point in the sky and say, okay, in what direction is the polarization changing? And so at this point in the sky, it's changing in this direction. And then you say, which way is the polarization? Well, it's at 90 degrees to that, or it's aligned with that. And you can say, okay, well, this fluctuation is an E-mode fluctuation. Go to some other spot in the sky and say, okay, what's the polarization? And so it's at this direction. And then which way is it changing? Well, it's changing this way, and that's at 45 degrees. So it's a coordinate invariant way to express changes in polarization. And what's weird about the microwave background is that in general, the cosmic microwave background only has E modes. So this is an E mode. So this is Stokes Q and U, which means it's tipped over at 45 degrees. So it's measuring polarization at 45 degrees. And you see that all of the structure is basically varying, has a tendency to vary either in this direction or this direction. And these are pure E modes, and this is real data. And so why is that? Well, it basically just comes down to the way that the microwave background is generated. That there were some fluctuations in that in the photons at redshift of 300,000. And so what caused those fluctuations? You basically just had fluctuations in the gravitational potential and what the universe was made of in different spots. But at every spot in the sky, you could just label it as a number. And so you get fluctuations in the microwave background where the conditions were changing. And so there's some direction that those fluctuations would change, but the way polarization was generated was just by Thomson's scattering. And so what that means is that the changes in the initial conditions source the fluctuations, and those changes were it was just some scalar field that was evolving, which means there's only one direction. If you write down a scalar field, or so we say gravitational potential at every spot in the sky, that's just a scalar field. And so that changes in some direction, and the polarization has only that direction to latch onto. So just from the symmetry of the problem, the polarization only has one direction to choose. It's either going to be aligned with that or at 90 degrees to that, but it's not going to pick 28 degrees, because there's no physics that picks that out. Whereas there are ways to get B modes. And the way to get B modes is by having something that has some orientation to it. And so what does that say? Well, it says you need another number. You need the conditions to be changing locally, but you need them to be changing in a way that has some direction attached to it. And how do you do that? Well, you could have some changing vector. You could have velocities. You could have some shear in the velocity pattern. If you could do that, then that would give you something that would be B mode. But there's no mechanism for getting shears in the velocities at redshift 300,000 that we know of, because the magnetic fields are small, and it's not clear where any of that stuff would come from. Or you could have gravitational waves. So gravitational waves are things that have some orientation to them. They have some polarization, just like photons do. So that's another. So that gives you another direction. So with gravitational waves, you can generate E modes. But just from looking at this, what you see is that the universe seems to be mainly E modes, which means the fluctuations were generated by some sort of scalars. So that's what people talk about when they mean scalar perturbations only generate E. It's just saying that there's no other direction to land on. So you can do this in Fourier space. Okay, so what I did is I took those Q and U maps, and you can combine them into an E map. And this is what we've measured. So this is when people do microwave background things these days, they'll often just present an E map. And so now no one has to tell you which way we've measured the polarization relative to. So now it doesn't matter whether my detectors were tipped over at 45 degrees. This is a coordinate invariant expansion of the polarization field. So these are the E modes, and these have been extremely well measured. So just as you can expand the CMB temperature power spectrum, you can expand the polarization power spectrum. And so here's the angular. So here's L again going from 10, there's 100, there's 1,000. So the last plot cut off sort of about there. And what you see is that in these E modes, what you see is you see the spectrum, you see lots of power that's been detected. It's not as high signal noise as the temperature because it's a smaller signal. But in B modes, we don't see anything. So here's a compilation of basically all the different experiments that tried to measure B modes. And what you see is that no one has measured some general power on the sky coming from these B-modes, which says that whatever the fluctuations are in the universe, they don't seem to have a very strong handedness to it. And so these are the upper limits. And then what's drawn down here, so let's zoom in on that, are some expectations of what the signal probably should be. And so here's a theory curve for what we expect the B-modes to be. And there's two lines here. There's this one right here. And this one right here is what we think the B-mode signal would be if there was a bunch of gravitational radiation kicking around at a redshift of 1,000. But the problem is you have to say, where did these gravitational waves come from? So it was before any structure formed in the universe. So any gravitational waves that there are in the early universe must have actually been effectively born in the Big Bang. So if you could actually measure the gravitational radiation coming from the Big Bang, you could actually have a direct measurement of the early universe. And so when we say the Big Bang, I'm meaning that period of inflation. Because anything that happened before that is a philosophical question, because all imprint of it has been wiped out. So it'd be really nice to measure this signal, because that would directly tell us what happened in the very first 10 to the minus 30 seconds of the universe. And we can measure that in the cosmic microwave background. What you see is that for this prediction, we're off by a factor of about 10 power. However, this curve has a completely unknown amplitude, because we don't know what happened in the first 10 to the minus 30 seconds of the universe right now. So we don't know how much gravitational radiation there is. That's something we want to measure. So this signal would be really awesome to measure because it gives us a direct measurement of the early universe. This signal is the one that we really, really, really think must be there. And why must it be there? Well, because we were talking about that pattern of E-modes and B-modes, but that's propagating through a lumpy universe. And as it propagates through the lumpy universe, photons get moved around. So even if you start with this extremely precise polarization pattern, it's going to get just muddled as it propagates through the universe, and photons jitter back and forth. And that's going to generate some amount of B-mode, and that's what this signal is. So this is the gravitational lensing of E-modes, but that has an extremely well predicted amplitude. But again, you see that this hasn't been measured. And so, but what I'm going to show you is that we've measured some of this signal. So that's the end of the talk, is that we've measured some of this signal. And the reason that's interesting, well, there's many reasons. One is that we're directly measuring the gravitational lensing, which means we can sort of map the universe in between. And the other reason is that it's saying that we're getting down to the levels where we can start to speculate about how large this signal is. So it's the first step in pushing down the signal so that we can start to try to figure out how much gravitational radiation was kicking around the early universe.
So what is the peak and value?
Which one?
The first
what are these peaks from?
Yes.
So that's because we see this in the photon field. So we see the gravitational radiation, and it's the same way that the peaks. It's the same way that there are peaks in the temperature field that are just coming from some horizon for the photons. There's a similar horizon for the gravitational radiation. They're the same photons, and they're coming from redshift of 1,000. So you're still going to get these ripples that are just coming from the acoustic oscillations that are sourced by gravitational radiation instead of from other effects.
So these are photons now.
So we're measuring the polarization of the photons, and the polarization of the photon. You only get a B-mode polarization of photons in the CMB if there's some fluctuation that is either has some orientation to it, either a vector or a tensor. So if you see a B-mode polarization signal coming from redshift of 1,000, it's clear evidence that there's either gravitational radiation at that time or some weird vector fluctuations. But in general, whatever's there, because it's been processed through these photons, you're going to get that sound horizon imprinted in those fluctuations. And so that's what you're seeing here. So it has a different. There's all sorts of details we can get into about that. The main thing to realize is that it's mainly this broadband shape with these ripples superimposed. But the ripples are not the interesting thing. The interesting thing is the existence of this signal. So the detailed shape of it would tell you a little bit, but Mainly what we want to know is how big it is and whether it goes up, whether it's sort of, whether it rises like this or whether it rises with some much steeper.
So these are gravitational wave ripples as opposed to acoustic wave ripples?
There shouldn't be any acoustic oscillations in the gravitational waves because they're not coupled anywhere.
So those are what the peaks are?
What was that?
These are gravitational wave peaks as opposed to acoustic peaks.
No, these are acoustic peaks in the structure sourced by gravitational waves.
Okay.
In the same way that, if you start with just some big lump of matter, or you have some big potential well, and just because the photons are going to have some sound waves from that, and in the same way, if you start with some propagating gravitational wave across the universe, that's going to cause ripples in the photons as it propagates through. And so that's going to get superimposed on this pattern. But the gravitational wave spectrum itself is completely scale invariant. In the same way the gravitational potential fluctuations are scale invariant.
You couldn't have beating of the gravitational waves?
You could set them up that way, but something would have to set them up that way.
Inflation.
You could have acoustic oscillations from inflation if you had some weird ripple in the power spectrum, but I've never seen a model for that. So you're on your way to being a theorist. All right. So here's our temperature survey. This is the intensity over 2,500 square degrees. So to give you a sense of how big 2,500 square degrees is, I put it on a piece of the sphere. So in general, it spans about 25 degrees, which is actually not, so it's not so much different than this. So it's sort of maybe about that big, and it goes from almost wall to wall, or probably exactly wall to wall. So that's the size of the sky that we've mapped, and that may seem like a lot, but compared to the whole sky, it's not that much. It's something like 7 or 8%. Okay, so but everything I've talked about so far is at redshift of 3,000 or of 1,000. So we're talking about the photon field at a redshift of 1,000, and those photons mainly came across the universe, but it was not an empty universe that they went through. So if you just sort of simulate the density contrast in, say, the dark matter or whatever you want to do at different times, so here's where the CMB was generated, and what you see is that the universe was extremely smooth. That's that part in 10 to the 5. Extremely smooth. And then, just as the universe evolved, what you start to see ripples. And 500 million years, you can see there's actually some large-scale fluctuations. And by the time you get to today, you expect the universe to actually be quite lumpy. So this is a simulation of about 1 billion light years across, something like that. And it's just taking some slice of that and looking at how much structure there is. And what you see, though, is that all sorts of interesting things have been going on in the universe. And so what can we say about that? Well, here's an example. These are interesting. Here's a zoom in on 4 degrees of our map, 4 square degrees, so 2 by 2. And here are these galaxies. Here's this cosmic microwave background. And these are interesting things that have happened in the universe. These are galaxies. There's a whole bunch of them. And so there's a galaxy and there's a galaxy. So you can see they're just emitting. And then you see this thing right here. And you think, well, that's funny. That looks like a hole in the sky. And you might say, oh yeah, you just masked that out, just like you masked that out in that SVT pole map. But no, this is actually a real hole in the sky, in the microwave sky. If you look at 2 millimeter data, 150 gigahertz, you're missing CMB photons there. Everywhere else it's 3 Kelvin, or 2.725. But this spot right here is not 2.725 Kelvin. This spot's more like 2.724 Kelvin. Which is a little weird, because all these other fluctuations are these large scale, so here it's a little negative, here it's a little positive, but there, it's like someone shot the sky. So that's a little weird. And so here's a zoom out, and there's that spot again. You can actually see, now you see all these galaxies, which are interesting. And then you say, yeah, that's actually a funny spot. And then there's a funny spot there probably too. And what are these little holes in the sky? What's going on? So, if you spend time in the US South, you think someone took a shotgun to the sign. But no. What it is a galaxy cluster. So if you take this spot right here and you point a telescope at it, and so you zoom in on this, and that's what these contours are this map, contoured. And right in the center of that, you see a whole bunch of galaxies. So what this is it's a big giant collection of galaxies. And and you think, okay, well, all those other dots, these dots are galaxies, and they're bright dots. Why is this dark? Well, it's because it turns out this dot, this hole, is not being caused by the galaxies. It's being caused by a bunch of stuff that surrounds these galaxies. And so this is what's known as the thermal Sanyaev-Zeldovich effect. So it's something I worked on for many, many years. So it's near and dear to my heart. But, so how does it work? Well, here's the CMB. If it goes through a cloud of hot electrons, then they'll interact. There's some probability of these things interacting. And the net result of the interaction is that this cold CMB, it's now 3 Kelvin, will start to thermalize with hot electrons. And that means that the electrons will cool down slightly and the photons will warm up slightly. So this nice black body curve that you started with gets warmed up a little bit. It means it conserves photon number, but moves to a slightly higher temperature. And so if you look down here at a frequency below the black body peak, what you see is you see a deficit of photons. So what that hole is telling you there's a big cloud of hot gas there. And that hot gas is just the gravitational compression of the general gas in the universe that's caused by the gravity of the dark matter and the galaxies that are there. And typically this signal for a big cluster is about 500 microkelvin. And so remember those CMB fluctuations were much smaller than 18 microkelvin. And that's what you see in this image. And what you see is that this is a very clear dot in the sky. It's a big, deep dent. So that's galaxy clusters. And so we have a bunch of these. So you find the dot in the sky, and then you go point your telescope at it, and you find a bunch of galaxies. And they're at different redshifts, redshift 1 or cosmological redshift 1.3. So you find a bunch of these clusters, and it turns out we found a bunch. So we found, so we've confirmed well over 300. So probably by the time we're done, we'll be almost up to 1,000 of these things. And they're spread out, they have all different masses, so they go from redshift of 0 to 1.2, so when the universe was smaller by a factor of half its size. And its mass is, the masses are typically around 10 to the 15 times the mass of the sun. So we have a bunch of them. So these blue points are all the ones we found. So we're not the only ones that do this. So with the Planck survey, the really bright ones, also you can see in the Planck maps. And then you can also see the X-ray emission from this gas. So we found a bunch of them. So if you want some galaxy clusters, come talk to me after. I can show you a few.
Why should that just like a small dot?
It's just the scale. So if I zoomed in enough, it would look big. But it's just because the typical scale of a massive collection of galaxies, so 10 to the 15 solar masses sounds like a lot. But our galaxy is about 10 to the 12 solar masses. So it's only about 1,000, it's a mass of about 1,000 galaxies. And so its size is typically a few million light years across. Whereas that map that I'm showing is more like 1 billion. So it's just, it's a small fraction of the, sorry, it's not 1 billion across, it's big. So it's just that, you know, an object that is made up of galaxies, something that's only a few million light years across, is just a tiny fraction of the sky.
The optical image.
Oh, that's zoomed in.
Right?
This is all zoomed in.
All the
Yeah. So, where was it? Yeah, so sorry, I should have made that clear. So, you know, so these contours right here are the contours of this. So this is 30 arcseconds across in the optical image. And 30 arcseconds is the resolution of our experiment is 1 arc minute. So this would be this whole image would be just a few, you know, would be about the size of this, maybe not even the size of this red circle. So that's why it's so small.
These maps are high pass filtered as well, right?
This map is somewhat high pass filtered. It's not optimally high pass filtered, but it's somewhat high pass. But you could actually see this dot in that first map that I showed. If you were to go back and look at it, you'd be able to see this dot there. So even when it's not filtered, it's still in there. Okay, so what do we do with it? Well, we try to measure dark energy, but I haven't, so if people are interested in dark energy, this is a way to measure dark energy, but let's keep going. So one thing that happens to photons is they run into electrons. The other thing that happens is they run into gravitational potentials. So here's a schematic of what's going to happen as a photon propagates through the universe. It gets sort of jiggled around as it propagates. And as it moves around, things are going to get stretched and moved. And the net result is that you start with some bundle. And as that bundle propagates through the universe, it gets moved, but it also gets differentially moved, which means a bundle of light rays is actually going to get stretched and sheared out in some way that's not entirely trivial. And so the net result is that you're going to look at some spot in the sky and you think it came from here, but actually as it propagated along the line of sight, it got jiggled around by gravity and it actually came from over here. So this is gravitational lensing of the CMB. So really what's, I can actually skip over that. So we can actually measure this distortion. So you can actually see that these things have been jiggled around by some amount. And what that does is we can take that temperature map, look for spots where the photons, where the CMB fluctuations have been sheared out and compressed, and make a mass map. So this is actually a map of the mass in the universe. So all of the mass between us and when the CMB was generated, which for all intents and purposes is all of the mass in the universe. And we can just make a map of how much is at every spot in the sky. Well, so we've done it over 2,500 square degrees. And so this is, the noise in this map is about 0.01 compared to the stretch, which is 0.05. So the bright spots here are 5 sigma. And that's saying that if you look at this spot in the sky, there's a mass fluctuation that's about 5 sigma. So it means there's a big lump of mass right here, somewhere in the universe. So if that's that spot on the sky, there's a big lump of mass. And at this spot on the sky over here, there's a big underdensity of mass. It's basically, and this is total mass. It's not luminous mass, it's not gas, it's not stars, it's total mass, which means the universe is mainly made of dark matter, which it is. Most of this is dark matter. So we have a map of all of the dark matter in the universe over 2,500 square degrees. So Planck can do the same thing, except they have an all-sky map. They're not quite as sensitive as we are, but they have the whole sky. So there's some spots like this that are the galaxy. So in this projection, the galaxy is around the outside. So they can't do very well near the galaxy, but these are spots of real mass in the universe. So here's our 2,500 square degrees. There's their all-sky map. And so if you're looking to know where the mass is in the universe, there it is. So we should actually talk to some astrologers, right? You can find out where the sun was compared to the mass.
It's different. Compared to the same patch.
So this is a signal noise of about 1. So actually, it's hard to tell what the same patch is on this, because I don't know which one is south and which one's north.
They are the same. They are the same.
Oh, these two are the same. You're right. So these two are the same. So
Yes.
this may just be the northern hemisphere. So I meant to put the southern hemisphere in the northern hemisphere, but I just multiplied the. So here's the SBT map. This is supposed to be the North Pole and the South Pole, but I just replicated them next to each other. No, that's funny. I never noticed that before. Okay, so what can you do with this? Well, one thing you can do with it is the same thing you did with the temperature map, which is just take the harmonic transform. And this is the CMB lensing power spectrum. So this is, again, just the multipole expansion. Here you see it goes from 2 to 2,000. And now you can see it's a lot noisier. So here's the Planck version, and these points on here are from SBT. So what you see is that it's a lot noisier, but this is actually real mass fluctuations in the universe, gravitational potentials, as illuminated by the CMB. So that's one thing you can do. And you could imagine if the universe has more or less structure, this curve will go up or down by some amount. And so it's a way to tell how much structure there is in the universe. So that's interesting. And what we can do with that is someday measure neutrino masses. So here's what this curve would look like as you crank on the neutrino mass. So neutrinos have some amount of mass. We know it has at least 0.06 eV, but we actually don't know much more beyond that, other than it's probably not a lot more than 1 eV. So it's a particle in this particle data book. It's the one where we don't really know the mass very well. So it actually affects cosmological structure formation, though, at a level of this curve will go up by something like you know, as you go from 0.1 eV to 1, you're seeing this curve is changing at sort of the 10% level. So if you can see already that this power spectrum is measured at a comparable accuracy to that spread. So it means that we're already sensitive to neutrino masses at the level of an EV. So you see that as, so in the Planck paper, they actually do limits on the neutrino mass. So this is an upper limit on neutrino mass. So this is likelihood of the neutrino mass. And what you see is that the neutrino masses probably are not 1 eV. And what's that? So that's saying, so a lot of that constraint, or a substantial part of that, is coming from this lensing constraint. All right. So we'll do better soon, but so there's more data coming soon. So here's our mass map. And again, I showed you that this spot here should be a big lump of mass, and this should be a big hole in the mass. And but so you can say, well, why don't we just look at that spot in the sky and see if we see a lot of mass there, or look at this spot and see if we're missing mass over here. And that sounds easy to do, except our telescope is at the South Pole, and the history of astronomy is dominated by sort of Europe and the U.S. for a long time, and building these big telescopes, and these big telescopes tend to be in the northern hemisphere. So with all these telescopes in the northern hemisphere, there actually are not very many big surveys of the southern hemisphere that have been done. And then when people started putting telescopes down in Chile, they said, you know what we should do is we should all look at the equator, because then everyone can see it. Surely everyone can see the equator, unless you're at the South Pole. So it didn't occur to them that people might put a telescope at the South Pole, and so there actually are not very many good surveys in the South. So in general, we've been looking around, and one thing we can look at is, so Herschel is a satellite that's flying and measures in the submillimeter. And so a 500 micron map, if you make a map at 500 microns, it has much higher resolution than this naturally. It actually has sort of a typical astronomy resolution, which would be some number of arc seconds. But on the left is the SPT lensing map. I zoom in on 100 square degrees of it. On the right is a smooth version at 500 microns. So this is just tracing the infrared emission of the universe. And that's the background. And the contours on top of this are just the contours from this map. And what you see is, you see that indeed where there's a bright spot in the microwave background lensing map, there's a bright spot in the infrared emission. And where there's a hole, there's a hole. And there's a hole and a hole. And so, you know, it's not perfect. There's something weird going on where there's a hole in the microwave background, but there's an excess in the infrared background. So that's interesting. That's saying that this spot is an interesting spot in the universe. What's going on there? Means that somehow that region is overly representative in the infrared background compared to what it is in mass. So that's telling you that this is a weird spot. But for the most part, there's all sorts of spots that line up. And that really is saying that, aha, we're actually getting some inclinations of how the infrared light, or submillimeter light, is related to the underlying dark matter. All right, so now we're going to get to the B-modes. So 2 expected sources of B-modes, and here's the one that you would think this would be the easiest one to measure because it's bigger than this one. So this one, we have no idea how big it is. It could be all the way down to 0. But this is the one that I think everyone agrees would be really great to measure. But if we can't even measure this one, we clearly have no hope of measuring this one. Right? So the first thing we need to do is get these upper limits down to the point where we can measure this signal reliably. So as I showed you, we have an E-mode map. And remember what I said this thing was. This signal right here is the lensing of these E-modes. So we have this E-mode map. We also have that cosmic infrared background map. And so we can do this many ways. We have our own mass map, which I showed you. But you can say, well, you know what, maybe you don't want to use all your own data. So let's use this infrared background map, that 500 micron map, to just estimate what the gravitational potential is. You saw those things lined up pretty well, right? So let's do that. And so let's take our measured E-modes, filter them a little bit. So this is a funnily filtered version of that previous one, but it's still the same data, it's just filtered a little bit. So let's take this map, assume that this is what the potential is, and then say, if we just lens this with this map, here's what the B-modes should look like. And so now what this is we have an actual prediction. We have a template for what the B-modes should look like in that patch of sky. And so we have a Bmode map that we can generate, and we never show it because it looks really noisy. So the reason that all these curves